Okay, welcome back. Section 9.2, L'Hopital's rule. We're actually learning something new today, so that should be interesting. Hold on one second. All right. So, L'Hopital's rule has to do, let's see if I can get this. There we go. Has to do when you end up with limits that are in something called indeterminate form. When you get 0 over 0, or when you get infinity or over infinity, or maybe you had negative infinity over infinity, those numbers are something that's called indeterminate form. They're actually pretty cool. It's not like undefined. Undefined is when you take 5 divided by 0. That's just an undefined number. If your limit ends up with 5 over 0, your limit doesn't exist, or it goes towards infinity. But indeterminate is kind of cool. It's actually when you get something like 0 over 0, then it's called indeterminate because you can't determine what the limit is just by looking at that. There has to be a few things that you can do with it. It's kind of cool. I would talk a lot about this normally. I could even maybe do a whole new video about it. But to try to keep this short to that 10 to 15 minute mark, I'm going to move on. So indeterminate form, when you have something like 0 over 0 or infinity over infinity. So here's an example. Like if f of x was x minus 3 and g of x was x squared minus 9, and I wanted to find the limit of f of x over g of x, that would, sorry, as x approached 3, that would just be this. F of x is x minus 3, g of x is x squared minus 9. If I tried plugging a 3 in, trying to plug a 3 in there, I'd end up with 3 minus 3 on the top, which is 0. See if this can do it. Oh, no. There we go. Which is 0. I can't type with this thing. Over, plug a 3 in there. 9 minus 9 is also 0. That's 0 over 0. That's that indeterminate form thing. Since it's 0 over 0, I can't really find it by substitution, but we already know how to solve something like this. We can use algebra. That x squared minus 9 can be factored. So if I factor that thing, it would end up being this. And that x minus 3 and that x minus 3 would cancel out, right? And so then you really end up with the limit as x goes towards 3 of 1 over x plus 3, but that you can use substitution for. You can substitute that 3 into there, you'll end up with an answer of 1 over, put in a 3 into there, 3 plus 3 is 6. That limit's 1 over 6. So we can find that indeterminate form limit. There's something kind of interesting about when the limit is in indeterminate form, when I get that 0 over 0. And that's finding a limit like this. You'll notice this limit is definitely not the same as that. This was the limit as x goes towards 3 of f of x over g of x. This is the limit as x goes towards 3 of f prime of x over g prime of x. Well, f prime, that's just the derivative of f. Derivative of x minus 3 is 1. G prime, that's the derivative of g. Well, the derivative of that would be 2x. So when it's asking for this, that's the same as asking the limit of 1 over 2x. 1 being the derivative of f, 2x being the derivative of g. I can plug a 3 right into there. Plugging 3 into there ends up with 1 over 2 times 3, which is also 1/6. The same exact answer as before. Now, the question is, does this always work? And the answer is yes, but only when you have limits that are in indeterminate form. So for instance, the limit as x goes towards 1 of this f of x over that g of x. That would be the same as the limit as x goes towards 1 of 2x plus 1 over x cubed, right? Just that's what f of x is and g of x. Here, though, I can plug the 1 in. I plug a 1 to the top, I get 2 times 1 plus 1, that's 3 over, plugging 1 in the bottom is 1 cubed, it's just 3 over 1. So 3 over 1 is just equal to 3, right? So this limit's equal to 3. It's not something in indeterminate form, it's just straight up equal to 3. If I tried that same trick as before and finding the derivative of each, right? The derivative of the top and the derivative of the bottom, well, the derivative of f, derivative of 2x plus 1, that's just 2. Derivative of g, so derivative of x cubed here, that's just 3x squared. If I plug a 1 in now, I end up with 2 over 3 times 1 squared, which is 2/3, which you'll note is not the same limit as we found before. So it turns out that if that limit is in an indeterminate form, if I have that 0 over 0 when I tried just substituting in, like over here in this one, when I tried plugging a 3 and I got 0 over 0, when that happens, the final answer for the limit is the exact same as if you took the derivatives and found that limit. That is something called L'Hopital's rule. So L'Hopital's rule says, if when you substitute for a limit, you get some indeterminate form, like 0 over 0 or infinity over infinity, then the limit you're trying to find is the exact same thing as a limit of the derivatives. It's a super, super helpful rule, L'Hopital's rule. Super helpful, because if I asked you to find this limit, that's a lot harder with algebra. Oh, sorry, never mind. This one says, always check to make sure L'Hopital's rules applies. That's actually, I'm glad I brought that up. I'm glad I made that mistake. One mistake with L'Hopital's rule is that people just assume, like, whenever you have a fraction, like, oh, I can just use L'Hopital's rule. You can't, right? So L'Hopital's rule, if I tried plugging a 0 in for this one, 1 plus cosine of 0. Cosine of 0 is 1, so 1 plus 1 is 2. Over plugging a 0 into there, sine of 0 is 0, so that ends up 2 over 0. That is not an indeterminate form. That's not a 0 over 0 form. So if I wanted to find this limit, L'Hopital's rule is not going to help me. This is just an undefined number. This limit probably actually goes towards infinity. You could check it graphically to make sure. But L'Hopital's rule definitely doesn't help me out. This one, however, this one we could do actually pretty easily with algebra, but instead of doing it with algebra, we're going to do it with L'Hopital's rule. So L'Hopital's rule, again, we're going to just check to make sure if I plug a 5 into there, that'll be 50 minus 50 is 0. Plug a 5 into there, 5 minus 5 is 0. I get that 0 over 0 form when I just try substituting. So what I can do is saying, instead of trying to do algebra, which again wouldn't be hard with this one, but instead of doing algebra, what I could say is, hey, well, since this is that 0 over 0 form, I could just take the derivative of the top and the derivative of the bottom and do that limit. So the derivative of 2x squared minus 50, that's 4x. The derivative of x minus 5, that's just 1. Now plug the 5 in. 4 times 5, that's 20. 20 divided by 1, answer is just 20. I don't have to go through all the algebra with L'Hopital's rule. I can just do the derivative, plug things in, get my answer right away. It's pretty slick. All right, this one. Oh, this one would be really bad. I don't even know how we'd solve this with straight up algebra, but L'Hopital's rule, it works slick. So again, just checking in here, plugging a 0. If I put a 0 in there, cosine of 0 is 1. 1 minus 1 is 0. Plug a 0 in the bottom, I also get 0. That is that 0 over 0 form. So that means L'Hopital's rule works. So I can find this limit by doing the limit of the same thing, but with its derivatives. Derivative of 1 minus cosine of x is sine of x. Derivative of x squared is 2x. And then I try it again, plug a 0 into there. Ooh, sine of 0 is 0. 2 times 0 is also 0. I get 0 over 0, which isn't an answer, but it is a number in indeterminate form. So guess what? We can use L'Hopital's rule again. Derivative of sine is negative cosine. Or sorry, not negative cosine, I'm crazy. Derivative of sine is cosine. Derivative of 2x is 2. Try and plugging in 0 now. Putting a 0 into cosine. Cosine of 0 is 1. So my final answer is 1/2. Turns out that this limit is just equal to 1/2 using L'Hopital's rule. A whole lot easier than trying to do that one algebraically. I would not want to attempt this algebraically. L'Hopital's rule, though, makes it really slick. Had to use it a couple times, right? I got 0 over 0, L'Hopital's rule, 0 over 0 again. Had to do L'Hopital's rule one more time, but it ended up getting an answer pretty quickly. All right. Side note, don't confuse the quotient rule with L'Hopital's rule. Notice here when I took the derivative, I took the derivative of that top, sine of x. I took the derivative of the bottom, 2x. I took it separately. I didn't do like the low d high minus high d low all over low squared. That's a whole different problem, right? If I asked you to find the derivative of this fraction, you'd have to use that quotient rule. L'Hopital's rule has nothing to do with the quotient rule. L'Hopital's rule just says, hey, if you've got that 0 over 0, you can take the derivative of the top separately, derivative of the bottom separately, and then you should end up getting the same value of your final answer for the limit. So don't confuse L'Hopital's rule with the quotient rule. They are completely different rules for completely different problems. Oh, we should have an example that has the form infinity over infinity, right? We've had that 0 over 0, so let's just try this one. Limit as x goes towards infinity of natural log of x, that's definitely infinity. As x goes towards infinity, x squared is definitely going to go towards infinity. So this is an infinity over infinity situation, but infinity over infinity is also an indeterminate form, right? So if you get 0 over 0, L'Hopital's rule works. So does infinity over infinity. So this problem here, L'Hopital's rule applies. I can take the derivative of the top and bottom separately. Derivative of natural log is 1 over x. Derivative of x squared is 2x. This limit would be the same as that limit. This one looks uglier right now, but it's not too bad. Using algebra, we can do a little bit of quick manipulation. This would simplify to that. I didn't do L'Hopital's rule again. I just straight up simplified it, right? If I multiply by x over x, right, put x times that would be 1, 2x times x would be 2x squared. So I can do some simplifying and make this thing look like that. And then when I think about the limit, it's actually pretty easy. I say, hey, I want the limit of this fraction as x goes towards infinity. But this is one of those thinker ones. You can do this pretty easy just thinking your way through. You're like, well, if this thing is getting bigger and bigger and bigger, I have 1 divided by something crazy huge and just getting bigger, that final fraction is going to get smaller and smaller and smaller, right? Like 1 over 200, 1 over 2,000, 1 over 2 million. It's going to get closer and closer and closer to 0. All right, we are just about done. It says use L'Hopital's rule only for limits of the form 0 over 0 or plus or minus infinity over infinity. It does not work for limits in other forms. That's the biggest thing I'm stressing. It's just like we talked about that very first one, whatever, over here. If it's not 0 over 0, L'Hopital's rule does not work. So just because you see a fraction, don't assume that means it works. It only works when you've got 0 over 0 or infinity over infinity. There is a side note, though we can sometimes use algebra to change forms into the 0 over 0 or infinity over infinity form. We'll save that for another day. That's something that we will usually teach when we've got you guys for an entire hour, but we're trying to keep it a little bit more brief. So today we're just focusing on when it's convenient. It's already in the 0 over 0 or infinity over infinity form. That shouldn't be bad for the AP test. I would really doubt they would do anything with L'Hopital's rule other than those 2 forms, especially this year with everything being kind of crazy. Good luck. As always, email me if you have questions, and miss you guys. Bye-bye.